Okay. This is the introduction of material from Chapter 4 of Zumdahl in Chemistry 101 that's going to be included on Exam 2, along with material from Chapter 3. The topic in Chapter 4 has to do with identifying different types of chemical reactions, and in particular, what happens in solutions with reactions, and how do we keep track of the amounts that go into the solutions and come out of the solutions, otherwise known as stoichiometry. Since we're going to end up talking about aqueous solutions, we'll begin by characterizing the aqueous part, water. Besides the obvious that water is an essential part of Earth, and sometimes it's called the water planet. Water is special in many respects. First of all, because it dissolves so many different substances. There are, to be sure, some substances that are hydrophobic, we say. They don't like water, such as oils, a good example. But water dissolves many things because many things and many substances are either ionic or polar. What do we mean by polar? Well, polar is a way of expressing a difference in a molecule between one side of the molecule and the other. And it refers to basically the distribution of electrons. So if the distribution of electrons around a molecule are uneven, then one side would be slightly positive and the other side would be slightly negative. And that is the case with water. And it owes to two different things. First of all, the polarity of the bonds. That is, in a chemical bond between two elements, unless they are exactly identical elements, then one of them will pull just a little bit stronger on electrons than the other one. And in this case, the pull is toward oxygen. And we use that symbol, an arrowhead with a plus sign on the other end. So that means this end is slightly positive. And we use this Greek letter delta, the small delta with a plus sign, to mean that it's slightly positive, but not full positive. It's not a full charge. It's just slightly in terms of redistribution of electron density. So the other end will be slightly negative. We can do the same thing for this one. All right? So that one is slightly positive, and that to balance things, that would make this one twice slightly negative. Okay? So for the water molecule, these bonds are polar, and due to the shape of the molecule, these polar bonds add up to an overall polarity for the entire molecule in that direction. So that's why water is depicted as slightly negative on the oxygen side, slightly positive on the hydrogen side.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
So, as a water molecule approaches a crystal of sodium chloride, we need to know something about the structure of sodium chloride. And you have sodium ions surrounded by chloride ions. And then if you focus on a chloride ion, you find that it is surrounded by sodium ions. So you get this network of positive and negative charges. Well, at the surface, in aqueous solution, the water molecule comes in, and if sodium, if that's the surface of the crystal, then the negative side of the water molecule is attracted to the sodium. And because other water molecules are out here, slightly negative, like this, then these other water molecules are also tugging on that water molecule that's trying to associate with the sodium. So there's a pull on that sodium. And when you get enough of these pulling, the force of attraction of sodium to water exceeds the force of attraction of sodium to the chloride ions in the crystal, and the sodium ion separates from the crystal, becomes surrounded by water molecules, and then we say it is in solution. So let's go through some definitions so that when we talk about solutions, we're speaking the same language. First definition is solute. Solute means the substance that is being dissolved. So in our previous example, sodium chloride would be the solute. It is being taken out of solid form and placed in aqueous solution. The solvent is that substance into which the solute goes. So in this case, that would be water. So the sodium chloride solute is dissolved in water solvent. Now, as a practical application, the solute is usually the smaller amount, and the solvent is the larger amount. And when you first start dissolving something, the solute in the solvent, that is the case. But there are some cases where the solubility, that is the amount of the solute that can be placed in solution, exceeds the total amount of the solvent. Perfect example is sugar water. You can dissolve table sugar in water up to and exceeding an equal amount of sugar to the water that it is being placed in. But by convention, we started off with a smaller amount of sugar, and even though in the end we've got more sugar than we do solvent, the sugar is still considered the solute. Now, another term that we need to define is the electrolyte. When you dissolve a substance in water and it separates into ions, at that point, the solution is able to conduct electricity because those ions are now mobile. So if you put a charge, a positive plate in one side, a negative plate in the other side, and it's pure water, nothing else but water, and you apply a charge to that, there's no conduction. Water is an insulator. It will not conduct a charge. But if you put ions in here, like with our sodium chloride dissolved in solution, then you can transfer the charge from one plate to the other because those ions are mobile. And those ions are called electrolytes simply because they will conduct electricity in solution. That's what we call an operational definition. Anything that will conduct electricity in solution is an electrolyte. Most often, electrolytes are substances that ionize when they're placed in solution. Sodium chloride is a perfect example. Other electrolytes you might even find in a blood analysis report that you've produced for your doctor to examine. They have a list of elements that are called electrolytes. And they exist in your body fluids. Sodium and chlorine are obviously two of them, but there are others like calcium, magnesium, potassium. Those are all considered electrolytes because when you place them in aqueous solution, they will conduct electricity. Now we'll go one step further. There is a difference between electrolytes and those that conduct electricity very efficiently when in solution, and those that do not conduct electricity very efficiently. Even though they do ionize, they ionize in a very small degree. Those are weak electrolytes. So if we place the light bulb in the circuit and used a battery with this solution, and we had a weak electrolyte in that solution, the light bulb would be very dimly lit. Whereas if we had a strong electrolyte in the solution with the same voltage, the light bulb would light up more strongly. And then, of course, anything that doesn't fit in to one of these categories is a non-electrolyte. And the light bulb would not light at all. Pure water is a non-electrolyte. Table sugar is a non-electrolyte. When you put table sugar in solution, it does not ionize. It goes into solution very well. And we'll, at some point in the future, explain why that is. But it does not ionize, so it cannot conduct an electric charge. Those are non-electrolytes. Oops. My mistake. Let's see. Okay, strong electrolyte, example. Here.
Strong electrolytes dissociate completely to give ions in solution that conduct electrical current. Soluble salts, strong acids, and strong bases act as strong electrolytes in solution. Weak electrolytes dissociate to a small extent to give only a few ions in solution available to conduct electrical current. Weak acids and bases are the most common weak electrolytes. Non-electrolytes are molecular species that do not dissociate into ions in solution. There are no ions available to conduct electrical current. Molecular compounds like alcohols and sugars are examples of non-electrolytes.
Okay. So if we're going to talk about the composition of a solution, we eventually have to get to the point where we're describing the chemical reaction that takes place in the solution, if any. Just because it's a solution doesn't mean that there's going to be a chemical reaction, but very often there is. When you place two or more substances in solution, they may react with one another. So we want to know things about what's the nature of that reaction. In other words, what are the reacting substances? How do they behave with one another? Do they remain in solution? Or do they turn into a solid that's not soluble? We call that a precipitate. And we also want to be able to quantify how much of each substance is in solution before the reaction and after the reaction. So we need some conventions. How do we describe the concentration of substances in solution? The most common, the most popular way to describe the concentration of a substance in solution is by molarity. Molarity is given the abbreviation M, big M. Big M is chosen because there are no symbols on the periodic chart that correspond to a single M. There are M's there, but they all have double letters. So we're safe with using a big M to represent molarity. And molarity is equal to the number of moles of the solute that is dissolved in 1 liter of solution. Moles of solute in liter of solution. That's the definition. So what we have here is a formula. Right? Just like any formula, any quantity, if we know the molarity and we know the moles, which I abbreviate as N, little n, this is not neutrons. Neutrons would have a 0 up here. Little n is abbreviation for moles. So the number of moles in the volume of liquid, and volume is in liters. If we know any 2 of those, we can solve for the third. Right? So if we know the number of moles and the number of liters of total solution, we calculate molarity. But if we know the molarity and we know what volume we have extracted from that container, we can calculate moles. It's simple algebra. So in this case, this example, if we have 6 moles of hydrogen chloride dissolved in solution of 2 liters total volume, we calculate 3 molar for the hydrogen chloride solution. Now, of course, when hydrogen chloride goes into solution, we already know that it goes into aqueous solution. We already know that it's got a different name now, right? If hydrogen chloride is in aqueous solution, it's got a different name now, right? Hydrofluoric acid. Okay? So now we know the concentration of hydrochloric acid in that solution. In this case, 3 molar. Let's take another example. Suppose we have a 500-gram sample of potassium phosphate. That's our solute, and we dissolve it in water, and the final volume is 1.50 liters. Okay, so we know the volume, 1.50 liters, final volume. That's after we add the potassium phosphate to water, and it's completely into solution, dissolved, and then the final volume is made up to exactly 1.5 liter. So that total volume includes both the solvent and the solute. We know what the volume is. We know what the mass is. It's 500 grams of potassium phosphate. So what we want to know is, what's the molarity? Can we do that with this information? Well, not directly, because we don't have any moles. We need moles. So how do you get moles from 500 grams of potassium phosphate? You have to do a conversion. First of all, we have to know what is the molar mass of potassium phosphate. If we know what's the mass of a mole of potassium phosphate, then we have a conversion factor that we can use to convert this into moles. First thing we have to do, we have to know what the formula for potassium phosphate is. That's essential. That's why I hammered nomenclature so heavy in the past. You have to be able to write these compounds correctly, or from now on, you're dead in the water. Potassium phosphate. There's potassium. Phosphate is a polyatomic ion. Now we know potassium comes from alkaline metals, group 1. So it has to have a +1 charge. No other possibility. Phosphate is a polyatomic ion. It has a fixed charge. all polyatomics have a single charge based on their name and their formula. 3-. So now we know that if we've got 3- charge here, how many positives do we need to balance that? 3, of course. Now we have our formula for potassium phosphate. How do you determine the molar mass for a compound? You add up the molar masses for all of the elements contained in the compound. So we need 3 potassiums. 39.10 rounded off grams per mole. And then phosphorus is 30.97. And then oxygen, we need 4 of them, right? 1 of these, 3 of these, 4 of those. Oxygen is 16, rounded up to 2 decimal places. So now we can find out what each one of those is and add them all up. 39.1 times 3 is 117.3 grams per mole. This one is 1 times that, 30.97 grams per mole. And this one is 64 grams per mole. Okay, so we add them together. And we get 212.27. Now, for those of you who are freshly out of Chapter 1, you'll notice that I've disobeyed the rules for adding and significant figures. This should be rounded off to 212.3, right? That's true if we were obeying significant figures. But I don't want to throw those two away just yet. We'll round off later, just so that we can minimize the effect of rounding error. So now that we have this value for the molar mass of that many grams, we can use that as a conversion factor, right? So many grams equal to 1 mole. So if we have 500 grams of potassium phosphate, and we want to convert that to moles, we need grams on the bottom, because this gram is on the top, and moles here on the top. So that means 212 goes on the bottom. So we divide 500 by that number, and I get 2.355. And that's moles. Okay, so notice that by doing this, I'm now rounded off to 4 significant figures in keeping with these 4, and this conversion factor goes out the window. In other words, those 5 significant figures don't count anymore. Only these 4 do. So now we have the number of moles, we've got the volume, we can calculate molarity. So let's do that. Moles and volume. So 1.50 divided into this is 1.57 molar. Now let's see if the slide agrees with my work. Okay, that's always good news. So in order to solve this problem, we went back to basics. What is the formula that has to be satisfied for molarity? Molarity equals moles divided by volume. What are we given? We're given the volume, no problem. We're not given the moles. We have to find the moles. So that is what took most of the work, finding the moles. Then the calculation is simple from that point on. Okay. Now, here's another problem that occurs in aqueous solutions with electrolytes. A compound that goes into solution, if it completely ionizes, will produce more moles of particles in solution than we would expect from the initial calculation. So what do I mean by that? Let's say we calculate that our solution is 0.25 molar in calcium chloride. So that means 1/4 mole of calcium chloride compound per liter of solution. But when we put it in solution, what happens to the calcium chloride? Well, it dissociates. We get 1 calcium and 2 chlorines, ions. So we started off with 0.25 moles of compound, but we ended up with 0.25 moles of calcium plus 0.5 moles of chloride. So now what's the molarity? Well, in terms of calcium, it's 0.25 molar because you've got 1 calcium for every calcium chloride. But for chloride, you've got 0.5 molar chloride for every 1 calcium chloride. So the total molarity of ions or electrolytes in this solution is actually 0.75, 0.75 molar in electrolytes. So here's another example. Suppose we want to find the greatest number of ions that are produced in these solutions. Well, here's where I invoke Henry Ford. Set up an assembly line so that you can do the same procedure over and over again. Get one of them right, be sure it's right, and then repeat it for the rest of them, and the whole problem will be correct. So we've got A at 400 milliliters of 0.1 molar sodium chloride. 400 milliliters of 0.1 molar sodium chloride. Okay? Question is, how many ions does that produce in solution? Well, we can find out how many moles of sodium chloride are produced because we know that our formula is molarity equals moles divided by volume. So if we want to find out how many moles of something, we just say solve for moles, and that's molarity times volume. Okay? Now, our temptation is to, well, actually, the instruction of the formula says this needs to be in liters. So if we convert that to liters, it's that. But since we're comparing these values for each one, A through D, we could multiply milliliters and be able to compare because the units of volume are the same for every one, whichever you prefer. I'm going to leave it at milliliters. That way I don't have to do any of those other conversions. So if we take molarity times volume, that gives us what? Well, 0.1 times that is 40. Right? 0.10. So that means I get 2. Well, what are the units on this? Well, don't panic. We have a new unit of measure. When we use milliliters instead of liters, then the product is now millimoles. And that's millimoles of sodium chloride. Okay, so now we can set up the rest of them and find out how many millimoles of each compound that we have, 300, 200, 800. Here comes the assembly line. I'm satisfied that that works. So I'm going to do all the other problems exactly the same way. 0.10. They're all the same concentration. They're just different compounds. This one is calcium chloride. This one is iron 3 chloride. And this one is sucrose. Okay. Test-taking technique. Question is, which has the greatest number of ions? Is there anyone in there that does not produce ions that we can eliminate? This one right here. Sucrose is not an electrolyte. It does not produce ions. So, save ourselves a step. The rest of them, we'll go ahead and calculate. So this one is 30, and this one is 20 millimoles of calcium chloride, and this is millimoles of iron 3 chloride. Now, that's the number of millimoles for each of the compounds. How many ions do we have? Well, this one produces 2 ions for every one, right? So we would multiply that one times 2 to find out how many ions. That is 80 millimoles of ions. This one has 1, 2, 3. So 3 times that would be 90 millimoles. And this one would be times what? 1, 2, 3, 4. 4 times 20 is 80. So this one produces the most ions out of all of those. Remember Henry Ford. Save yourself a lot of heartache. Just be sure one of them is correct, then do the rest of them exactly the same way. Just changing conditions based on what compound we have. But the series of steps are identical. Okay, this is the author's idea of solving problems. And as I always say, in this case, we're saying, where are we going? Well, where are we going means, what's the question? What's the question is, what's the greatest number of ions? The greatest number ions. Then you look at what you're given. That's what we did over here. We said, okay, we're given volume, we're given molarity, we're given the compound. Okay, in order to answer the question, we needed to solve for this one, because we're given molarity, we know what the relationship of moles to volume is. So that's all we needed to do, solve for moles. And then we solved for moles of compound, and then we had to deduce how many ions were produced for each one of those compounds. And that gave us the final solution. And then check yourself to see if it's reasonable. And I see nothing wrong with what we've done so far. Okay. Now, here's another procedure that especially lab techs have to perform. It's called dilution. When we prepare solutions, it's usually a very tedious process. So what you want to do is prepare enough solution to last for a great number of procedures, in the hundreds. The problem is, if you prepare enough solution for 500 or 600 analyses, you're going to have 30-gallon bottles scattered across your bench top. So what you do is you prepare a concentrated solution that you know precisely, accurately, I should say, accurately, the concentration. And then whenever you need to use, you need to make a working solution that's going to enter into your procedure, you take the stock solution, we call it, the concentrated solution, and you dilute it. so that it will give you your working solution concentration. Then you only have to keep a small bottle of the concentrate and just quickly make up a diluted solution to work with. Now, before we get on to that, let me say, how do you prepare a solution? We've gone through the definition of molarity, moles per volume. But what does that mean in a practical bench chemistry situation? For instance, suppose I want to prepare a solution of a substance. We can call it anything you want to, sodium chloride, right? And I know that I want to make up 1 liter of that solution. So I established beforehand that my final volume is equal to 1 liter. What else do I need to know? Well, if I'm preparing a solution of known molarity, I may say, well, I want a 5 molar solution. Okay, so now we have 2 terms, we can find the third. So molarity times volume, this one times this one is 5 moles of sodium chloride, right? Do we have any balances in our lab that will measure in moles? No, they measure in grams. So we have to convert the moles to grams. Okay, sodium chloride would be the summation of 23 for sodium grams per mole, and chloride is 35.45 grams per mole. So sodium chloride is 58.45 grams per mole. So 5 times that would be the mass that's required to make that solution. Uh, 292.25. Okay, and again, I'm ignoring significant figures because I want to minimize rounding error. So if we weigh out this much sodium chloride and dilute it to 1 liter volume, we will have a 5 molar solution. So how do you do that? Well, we have our vessel. That's my drawing of a volumetric flask. A volumetric flask is a long neck flask with a big bulb at the bottom. It has this long neck on it because we want to be able to see the movement of the liquid as we fill it. And we want to know exactly when we have 1 liter. This flask is calibrated, so that position is exactly 1 liter. So we put this in here with a little bit of water, and it sits on the bottom in a mass, so we have to stir it, right? And we stir it and stir it and stir it until it goes into solution. And with most solution processes, the temperature is going to change. It may get hotter, it may get colder. But what happens to a liquid when you make it hotter or colder? If you make it hotter, it expands. If you make it colder, it contracts. So you cannot rely upon that volume unless it's at the temperature for which that volume was calibrated. And these calibrations usually occur at 25 degrees centigrade. Now, as a practical matter, if the temperature is not more than a degree or 2 off, either way, you're safe. The change in volume is not going to be that much for just a couple of degrees. But you don't want to put something in there that increases the temperature by 30 or 40 degrees centigrade and then dilute it to volume, because when it cools to room temperature, what's it going to do? It's going to shrink. Or if you make it cold, like 20 or 30 degrees colder, and you fill it up to that mark, what's it going to do? It's going to expand. That's the problem. If it expands, you've got no recourse. If it shrinks, you can just bring it to the mark when it's cooled to room temperature. But practically speaking, a good bench chemist will make this initial solution and then maybe dilute it to up here with water. Once it's dissolved, and dilute it to that mark, and then mix it really good, let it sit on the bench. You know, cover it with something like parafilm, or put the plug in it, put the stopper in, and let it come to room temperature. It may take an hour, 2 hours, whatever it takes. Once it's come to room temperature, then you finish adding solution to the mark, put the stopper back in, and mix it. Now you have a solution of sodium chloride that is 5 molar. Okay? That's some practical chemistry. Now, suppose we have that solution that's 5 molar. It can be sodium chloride, it can be anything. That's our concentrated stock solution. We want to make up a solution that's 1/10 molar for performing our experiment. So we want to take this one and we want to dilute it somehow to 1/10 molar. Oops, I've been accidentally punching the button, haven't I? Okay, set that aside. Here's the theory. We've got this container of 5 molar solution. Okay? We want to come over here and make a solution that's 0.1 molar. All right? So think about this. What do you want to do? You don't want to put the whole amount in there, right? That doesn't serve the purpose. You want to take part of this out, put it over here, and add more solvent. And as you add more solvent, the solute becomes more dilute. Okay? That's the qualitative description. Quantitatively, what we want to do is know exactly how much to take out of this that will give us the right amount over here, producing that concentration. Okay? So what do we need to know? Well, molarity equals moles divided by volume. If we know the molarity, and we know the final volume, let's say it's another liter. Then we need to know how many moles to put in there, right? So solve for N, we need to know, we need to have 0.1 mole of the solute. So how do we get 0.1 mole of solute out of this? Use the same relationship. Okay, we know that we want 0.1 mole here, and we know the molarity here, right? So now we can solve for the volume. How much volume out of this will give us 0.1 mole to satisfy the conditions on this side? So we solve for volume. So volume comes over here. Molarity goes down here, and we have 0.1 divided by 5. This is moles, this is molar, and it's messy. Here we go. So 0.1 divided by 5 is what? Well, 1 divided by 5 is 0.2, so 0.1 divided by 5 is 0.02. liters. So we need to take 0.02 liters out of here, put it over here, and dilute it to 1 liter. But glassware is not calibrated for small amounts in liters. It's calibrated in milliliters. So how many milliliters do we need? Well, we move the decimal place 3 places to the right. So 1, 2, 3. So that's 20 milliliters. 20 milliliters of this solution diluted in that solution to 1 liter will give us that concentration. Okay? Now, all this talking I've done has been based on one premise. The moles you take out of here are the same moles you put over here. And if we solve this for moles, we get N equals MB. So on this side, this is our second situation, or the diluted situation. This is M diluted times V diluted equals the number of moles. But that N is the same N for over here. And over here, we have M concentrated times V concentrated equals moles. So those two are equal, because if this is equal to that, and that's equal to that, then this is equal to that. That's where M1V1 equals M2V2 comes from, because N equals N. All right. So as a practical matter, how about this one? 0.5 molar solution of sodium chloride is in an open beaker, sitting out on your lab bench, which is kind of stupid to begin with, but this is hypothetical. Which of these following scenarios would decrease the concentration of the salt solution? Right? Decrease the concentration means less solute per volume. If we add water to the solution, would that decrease the concentration? Yes, of course it would. If you add water, you're increasing the solvent concentration. You haven't changed the amount of solute, so it is distributed throughout a larger volume, making it less concentrated. That one does decrease. Pour some of the solution down the sink drain. What does that do? That has nothing to do with concentration. Remember, concentration is an intensity factor. In other words, it doesn't matter how much of the substance you have, concentration doesn't change. Add more sodium chloride to the solution. What does that do? You got the same volume, but you have more solute. So that increases the concentration. That won't work. What if we let the solution sit out on the bench, open to the air for a couple of days? What happens? The water evaporates, right? If you reduce water, that's the solvent. You're increasing the concentration of sodium chloride, which by amount stays the same, but we're reducing the solvent, so the concentration increases. That doesn't work. At least two of the above decrease the concentration. No. Wait a minute. Add water. Right. This is the only one. A is the only one that decreases the concentration. Okay. Let's see if we need to spend time on this one. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? Okay, so this is a an M1V1 equals M2V2 problem. Now, that's a very useful formula, but it has one pitfall. When you read a problem like this, you have to know exactly which side those numbers go on. Which ones belong on the M1 side, which ones belong on the M2 side. So you've got to be sure that the molarity in this case matches up with the volume of that molarity. And the molarity here matches up with this volume. So which ones match which? Well, let's say we want to have, the question is, what volume of 2 molar sodium hydroxide? So let's say volume 1 is the question for molarity of 2 molar. Okay? That leaves volume 2, 150 milliliters, and 0.80 molarity. Okay, now we have it set up correctly. These two go together, these two go together. Now, remember when I did not change milliliters to liters? In this case, it's perfectly valid to keep the milliliters rather than changing them to liters. And here's why. Let's rearrange this thing. We can do that, algebraically speaking. The math is perfectly valid. If we put these two together, M1 over M2 is equal to what? V2 over V1. Okay? Now, what are the units here? Well, this one's molar and this one's molar. They cancel, right? This one is what? Well, typically it would be liters, right? Liters, liters. They cancel. What if we decide to use milliliters? They cancel too. So, ratios like this, you don't have to change the volume. Right? If you're using the pure formula, you may have to change the volume, unless you recognize that if you use milliliters here instead of liters, you're talking about millimoles. Millimoles divided by milliliters is molarity. Now, I don't have time to prove that to you. Take my word for it. You can prove it to yourself. Okay, so we can leave the volume, in this case, at milliliters, which means when we solve the problem, the volume is going to be in units of milliliters. Right? That's convenient, because milliliters is probably the measurement we want to use when we do the dilution. So, 2 molar times V1 equals 0.8 molar times V2. Right? So solve for V1. It is 0.8 times 150 divided by 2. And I get 60 milliliters. So we measure out 60 milliliters and dilute it to 150 milliliters, and the product is 0.8 molar. Okay, types of chemical reactions. Chemical reactions, for categorizing chemical reactions is convenient, because if you know what type of chemical reaction is, it can direct you toward the ways that best describe the system. In other words, if we know it's a precipitation reaction, we know that when we put these two solutions together, they're going to react and produce a solid. It's going to drop out a solution. So that says All right, if you want to collect that solid, just filter it, right? Then dry the solid, and there you go. If it's an acid-base reaction, maybe we want to know exactly how much of acid is combined with that base, and we'll use a pH meter or a color indicator to tell us when the equivalence has been arrived. Or if it's an oxidation-reduction reaction, we may want to use that for making a battery. That may not make sense now, but it will in the future. These are major types of chemical reaction. The other point is that many reactions can be characterized by more than one of these. We could have an acid-base reaction that produces a precipitate, or we could have an oxidation-reduction reaction that also serves as an acid-base reaction. There are many other types of descriptive terms for reactions, but for now we're going to focus on these three. Okay, so a precipitation reaction typically takes the form of a double replacement reaction in which a solid forms. So generically speaking, if we have a compound that's a cation and an anion combined with another compound that's a cation and an anion, and they're both soluble, right? They start off in solution, then we combine those two solutions. We'll get a double replacement reaction. In other words, the A replaces the C and the B replaces the D. So in order to do that, we just take the A and substitute for C, and we get CB plus AD. Now, typically what happens is one of these compounds remains in solution. Let's just pick this one. But this one becomes insoluble. It becomes a solid. And you see it as an opacity to the solution. And over time, you'll see it settle to the bottom of the solution because it's insoluble. It just sinks. Now, why does this happen? Well, it happens because most of these compounds that react are ionic. So in aqueous solution, we actually have this one, this one, this one, and this one in solution. So that means they have an opportunity to interact, right? If they were dissolved as the molecular substance, it would be more difficult to get an interaction between those two. Not impossible, but difficult. If they form ions, then they're free to interact. So A interacts with D and B interacts with C, and you get that product. That's a double replacement reaction with a precipitate. Here's an example. The authors wrote it poorly because they've jumped over several steps. They've gone to the point where they've only taken one cation and one anion from the mixture and said, this is what those two do. They interact, produce a solid. That's only part of the reaction. That's not the complete reaction. So I'm just going to skip this one because I think it's confusing.
Silver ions react with chloride ions to form the precipitate silver chloride. In this animation of a precipitation reaction, the silver ions, shown in gray, and the chloride ions, shown in green, are active participants in the reaction and combine to form the insoluble silver chloride crystal. Other ions, called spectator ions, shown here in blue and purple, are not participants in the reaction and remain unchanged in the solution.
So a precipitation reaction begs the question, why does the precipitate form? The simple answer is the attraction between the cation and the anion in the precipitate is much stronger than the attraction of either of the ions for the solvent or water. That's the short version. So when we get a precipitate, it introduces some new terms. A precipitate is described as insoluble. That is, the solid does not dissolve in solution. Whereas anything that remains in solution is soluble. And we put this AQ next to it to designate that it is in aqueous solution. Now, the truth be known, most insoluble substances are really slightly soluble. So this is a general division. And it's useful because most of the insoluble substance is going to be the solid. But there are always a few ions that remain in solution. And we'll have to deal with that in a later chapter when we talk about equilibrium. But for now, soluble versus insoluble is a useful designation. Now, how do we define solubility as a practical matter? Okay. These are, we can approach solubility in two different ways. One is a set of rules that guide us through the process of determining whether a cation and an anion in solution will form a precipitate or remain in solution. So that way, this set of rules says that nitrates are soluble. It says most nitrates. I would argue that all nitrates are soluble. Second rule is most alkaline metals are soluble as salts, as is ammonium as the polyatomic ion. Now, what are the alkaline metals? Well, they're the group 1s, right, over here. All of these are soluble. Now, as we go down through this list, the order is important. If you ever encounter a conflict between one rule and the other one, the rule above it takes precedence. So if we had a conflict between this one, most sulfate salts are soluble except for barium, lead, mercury, and calcium sulfates. If we had a conflict between that and, say, this one, you know, this one would take precedence. Most chlorides, bromides, and iodides are soluble except for silver, lead 2+, and mercury 2+. Skip that, we've done this one. Most hydroxides are only slightly soluble, except for sodium hydroxide, potassium hydroxide. The barium hydroxide and calcium hydroxide are marginally soluble. So there are some differences there that have to be considered in any scheme where you use solubility as the guiding principle. Sulfides, carbonates, chromates, phosphates. All of these are only slightly soluble, unless they're combined with alkaline metals or ammonia. Then that makes them soluble. See, so in that case, 2 takes precedence over 6. All right, those are the rules. The other way to deal with it is with a chart. And if you go to the review document that I handed out in class or is available on Blackboard, you'll find out that on the back page, one of the back pages of the review document, you have this chart. And down the left-hand side are the anions, the negative ions. Across the top are the positive ions. And to combine an anion with a cation, you just find the ones that you're interested in and follow them until they meet. And the block where they meet, if it's grayed out, they're insoluble. Whereas if it's clear, they're soluble. This will be included on the exam, along with the rules that are at the bottom of the page. So if you were going to be chemists, I mean, bona fide bench chemists, you know, not part-time chemists, then you would have to memorize these rules and use them rather than this chart. But if you use the chart often enough, then these rules, and you run into these examples, the rules sort of embed themselves. So eventually you'll know the rules whether you like it or not, if you do enough of the problems that use the chart. Okay, which of the following ions form compounds with lead 2+ that are generally soluble in water? Right? Test-taking technique, look for the ones that are impossible first. So, which one of these, if any, cannot form a compound with lead 2+? Any other cation, of course. Cations repel one another. They will not react. So you can throw E out right off the surface. Now, how about solubility? Well, we know that all nitrates, according to Rule 1, all nitrates are soluble, right? So C has to be one of them. Chlorides are generally soluble except for what? Well, silver's one of them. Lead's another one. It's insoluble. Sulfides are generally insoluble, as are sulfates. So really, the only one that's soluble is the nitrate. Now, that's based on the rules. But if you use your chart, you could run down lead, which is over here next to the last, run down here and check each one and find out that the only one out of that group that's soluble is nitrates. Okay, when we write a chemical formula and an equation using those chemicals, they can come in 3 different forms if we're describing a double replacement reaction. This is one example. Silver nitrate in aqueous solution is added together with sodium chloride and yields silver reacting with chlorine, which is insoluble, and nitrate reacting with sodium, which remains soluble. Okay? That's what's known as a complete molecular equation. Well, no, that's not true. Reserve complete for later. That is the molecular equation. I abbreviate equation that way. So the complete equation is this one, which is soluble because it's a nitrate, and this one, which is soluble because it's a group 1 compound. And then when they react, they produce this one and this one. That one's soluble because it's got an alkaline metal and a nitrate. Okay, But what's actually going on in solution? The complete ionic equation will show you what is happening in solution. This is soluble, so this breaks up into individual ions. Silver ion in solution plus nitrate ion in solution plus sodium ion in aqueous solution plus chloride ion in aqueous solution. That's why they can react, because they are electrolytes. So what do they produce? Well, they produce this solid, right? It doesn't change. It's a solid product, so it stays the same. It does not break apart. But we still have sodium ions and nitrate ions in solution. Okay? That's the complete ionic equation. Now let's look at this. What do you have here? Well, I notice that you have sodium on both sides. Now, just because we have this arrow here doesn't mean they're separated physically. These are the same sodium ions as reactant as the sodium ions as product, and they're in the same vessel. Right? There's no change. They're there to start with, they're there at the ending. This is a spectator. It doesn't react with anything. The same holds true for the nitrate. It's also a spectator. Right? Same nitrate here as over here. Now, what does it look like when we remove the spectators? Because they're not part of the reaction. We get the net ionic equation. So we take out these, that one cancels that one, and this one cancels that one. And what are we left with? We're left with this one plus this one yields this product. Okay, that's the net ionic equation. Now, why would we ever want to describe a reaction as a net ionic equation? Well, I can think of one practical application. Suppose we go back in our laboratory, we want to produce silver chloride, but we don't have any silver nitrate, right? Well, what else is soluble? Well, let's see, there are several possibilities. Nitrate's the best one, but suppose we only have silver acetate. Will it still be soluble over here? Sodium acetate is soluble. C2H3O2. Right? So now we have acetate instead of nitrate. Will the reaction be the same? Exactly the same. You'll still react silver with chloride and get silver chloride. Suppose we don't have any sodium chloride. We may still have a nitrate, but suppose we only have potassium chloride. Well, substitute potassium. Potassium nitrate is soluble. Potassium acetate is soluble. So they don't react, and we still get the same net equation. So that's one practical use of the net ionic equation. It removes all the fluff and leaves you with only the meat of the problem. So you need to be able to do that. Write the molecular equation, then break it apart into its complete ionic equation, then cancel out spectator ions and give me the net ionic equation. There's your complete ionic equation. There's your net. We just remove the spectator ions. Here's another example. Cobalt chloride, sodium hydroxide yields cobalt hydroxide, which is insoluble, sodium chloride, complete ionic equation. Get rid of the spectators. What are the spectators? Well, look at what's part of the reaction. Cobalt and hydroxide. So we keep cobalt, we keep hydroxide, and we get rid of the chloride and the sodium. Oops, that's not right. That is not right. That is a mistake. And will be corrected in the next presentation. Let's see, where is that? That's a major boo-boo. That needs to be 2 hydroxides. Okay, we'll fix that. This needs to be OH minus, right? You can't react cobalt to chloride and get hydroxide. That transition is not possible in chemistry. So, when you have a solution equation and you're interested in what goes in and what comes out, quantitatively speaking, you want to know something about solution stoichiometry. Solution stoichiometry is not much different than the stoichiometry we've covered so far. It's just that when you have an equation, you cannot proceed from one part of the equation to the other unless you're talking about moles. So a previous example in chapter 3 we had was we had mass of one reacting with a mass of another reactant, and we wanted to find out how much product was produced. In order to do that, we had to convert the mass to moles, which is simple. In solution stoichiometry, you're usually giving a certain amount of solution and its concentration. And we know from this relationship, we can calculate the number of moles. So it's just a matter of getting to moles by a different route. Okay. So these are ideally steps in solving a solution stoichiometry equation, problem, excuse me. You want to know the species that are present in the solution and determine what reaction occurs. Right? We've just discussed a double replacement reaction, which is going to be the common theme for solution stoichiometry. Write the balanced equation, molecular equation, and complete ionic, and then net ionic equation. If you write the net ionic equation, then you can simplify your problem to just those species that are going to react, right? Because if you have a complete ionic equation, and you put in something that's soluble before and after, you're going to have the same amount after as before. Then you calculate the number of moles of reactant or product, whichever the problem insists upon, because you may want to go from product back to reactant. So this is an example where you're going from reactant to product. Then you need to determine which reactant is limiting. Right? If you've got two reactants that you're putting together, of course, you're interested in which one runs out first. And then based on which one runs out first, you calculate the number of moles of product as required. And then if necessary, convert to grams or whatever other unit is required to answer the question. Now I'm thinking that chapter 3, let me check for just a second. There's a possibility that we did not get to the end. Let me be sure. No, we did. Right. But we're going to cover in the review session, next time we meet, we're going to take up problems that involve limiting reactants. I think we need a little more work with those. So we'll hammer those pretty hard during the review session. And how to determine the limiting reactant, what you do with that information to solve the problem. So, let's see, where are we? We're still talking about precipitation reactions. If you have 10 milliliters of 0.3 molar sodium phosphate solution reacted with 20 milliliters 0.2 molar lead-2 nitrate solution, what precipitate will form and what mass of precipitate will form? Okay. The precipitate that forms is the simpler question. So the first thing you need to do is you need to write the reaction. You got to write the compounds that enter the reaction because they're only given by name, right? So we're back to nomenclature. Take that name and write the compound. So we've got sodium phosphate, which is 3 minus, so we need 3 sodiums in solution. Then we have lead-2 nitrate, lead, it's a 2 plus, and nitrate is a 1 minus, so we need 2 nitrates, okay? In solution, nitrates are all soluble. Okay, so what do we get? A double replacement reaction will put sodium with nitrate. Sodium nitrate is still soluble, right? Alkali metal, nitrate, it's soluble. Lead phosphate, though, lead-2 phosphate, this is a 3 minus, that's a 2 plus. So we cross multiply and we get 3 here and 2 there. So now our compounds are properly balanced. Now we need to solve the equation. We need to balance the equation, pardon me. And if we go through our budgeting process, and I think I'll do it for this one, just so that you can see it done for a more complex reaction. We see that we have polyatomic ions that are the same on both sides. Nitrates, phosphates are the same. So they can be used as separate units. So we have sodium here, phosphate. I'm not going to write the charge in. Lead and nitrate. Okay, so how many sodiums do we have to start with? 3. Phosphates, we have 1. Lead, we have 1. And nitrates, we have 2. Now on this side, we have 1 sodium, 2 phosphates, 3 lead, and 1 nitrate. Okay, where do we start? Well, you can start at the top. That usually works. So if we make a 3 over here, that gives us 3 sodiums, takes care of the sodiums, but it also changes 3 nitrates. Okay? Now, phosphates. We have 1 here and 2 there. So if we have 2 here, that gives us 2 phosphates and 6 nitrates. Okay? Now how about lead? We got 3 leads over there, we need 3 over here. So that's 3 leads, and that's 6 nitrates. Excuse me. 2 phosphates. Wait a minute. 6 sodiums. My mistake. That should have been 6 up here. Now it's 6 down here. Okay. My apologies. So now we need 6 nitrates. So we change this one to 6. That gives us 6 nitrates. It also gives us 6 sodiums. And now we're balanced. 6, 6, 2, 2, 3, 3, 6, 6. So now our equation, our molecular equation is balanced. So let's clean this up. That needs to be a 6. We don't need charges right now. We will have to remember them, but they're not necessary in the molecular equation. 3, 2. So there's our molecular equation. What precipitate forms? Well, lead phosphate is insoluble. All you have to do is check your chart. Lead and phosphorus, lead 2 and phosphorus are precipitate. Okay, so that gives us the answer to that question. What mass of precipitate will form? For this equation, we need to do stoichiometry. 10 milliliters of 0.3 molar, 10 milliliters of 0.3 molar are reacted with 20 milliliters of 0.2 molar. Okay? So, how many moles of this one do we produce? How many moles of that one? How many moles of this one are reacted? How many moles of this one are reacted? It's molarity times volume. So in this case, I do want to have these volumes in liters so that the result is in moles. We're going to work with moles in this case. So this one is equal to 0.010 liters, and this one is equal to 0.020 liters. So if we multiply this one times that one, will tell us how many moles of this we start with. So this one is 3 times 10 to the minus third moles of that compound. And this one, that one times that one, is 4 times 10 to the minus 3 moles, I think. Yes. Okay. So the next thing we have to do is find out if you're given a definite amount of each reactant, you can assume 99% of the time, unless it's a theoretical problem, that one of them is going to run out first. That's the limiting one. And that one tells you how much of the product is available or will be produced. So how do we do that? Well, we assume that all of this one reacts and produces lead-3 phosphate. Okay? So what is the conversion? Well, if we have this much of that compound, look at the ratio. One of these for every 2 of those, right? So if we convert this to, well, it's not right. Two sodium phosphates for every 1 lead-3 phosphate. Lead-2 phosphate, excuse me. Right? So we divide by 2, and we get 1.50 times 10 to the minus 3 moles of lead-2 phosphate. Okay? That's if everything is used. What happens with this one? If we use this one, then the ratio is 3 to 1. So in this case, we have, for every 1 of these, we have 3 of these. right? So 3 into 4 is 1 point something. 1.33. 1.33 times 10 to the minus 3 moles of lead to phosphate. That's if everything reacts. Here, you get that much. If everything reacts here, you get this much. So, which one is the limiting? The limiting one is the one that produces the smallest amount of product. This one. That's the limiting one. This one is excess. Okay? So, now that we know that we have this much potential, this is the actual amount of lead-3 phosphate that will be produced, we know that this many moles produced. Now all we need to do is convert to mass. So how do we convert to mass? We need molar mass, grams per mole. Cancel those moles, grams per mole of this one. So we need 3 times lead, 207.21, and 2 times phosphorus, 3097, and 8 times oxygen. So that would be the molar mass of our lead-2 phosphate. I get 811.57 grams per mole. So 811.57 grams per mole. So that number times this number gives us 1.08 grams of lead-2 phosphate is produced from this reaction. Let's see if I get the right answer. Close. Rounded off to 2 digits, 1.1 gram. Okay? So that seems like a lot of work, and it is, but you need to approach it logically. Whenever we talk stoichiometry, the cardinal rule, well, first cardinal rule is write your compounds correctly. If you can't do that, you're dead. Then balance the equation. Then, in the case of solution stoichiometry, what is your precipitate? Because that's where the reaction is going to occur between these compounds. Then you have to, before you can go anywhere in this equation, from here to there, there to there, you have to have moles. Grams won't do it, milliliters won't do it, you have to have moles. Once you have moles, then you can do comparisons to see which one is limiting. And after you find the limiting reactant, that one determines how much product you get. Okay. This is a trick question. If we have this much sodium phosphate reacting with this much lead nitrate, similar to these two, what is the concentration of nitrate ions left in solution after the reaction is complete? First of all, you ask yourself, is the nitrate part of the reaction? No. Nitrate's a spectator. So in order to determine the concentration, all you need to know is how many moles of nitrate and what's the final volume. Then you can calculate the concentration. So here's the nitrate. You got this many moles of that compound. So how many moles of nitrate do you have? You have twice as many, right? For that compound, for every 1 mole of this, you got 2 moles of that. So you actually have 8.00 times 10 to the minus 3 moles of nitrate. Before and after, because it does not react. Okay, so what's the final volume? The final volume is a combination of these two because you mixed them together. So you've got 10 milliliters plus 20 milliliters is 30 milliliters. How much is that in liters? You go 1, 2, 3. And don't forget your leading zero. That's one of my pet peeves. I don't want to see any orphan decimals. If you've got a decimal sticking out here to the side, to the left-hand side, it better have a zero bracketing it. Liters. Moles per liter. So 8 divided by 0.3, I'm not going to waste time on the calculation, is 0.27. Molar nitrate. Okay? So here's the author's idea of solving the problem, which is fine. This one is a little more complicated. What's the concentration of phosphate ions? Well, we've worked the problem up to this point, and we've used up some of the phosphate, right? We've produced lead 2 phosphate. So we've consumed some of this, but notice this is excess. So there's going to be some phosphate left over. How much phosphate left over? Well, it depends on how much we used. How much did we use? Well, if we used this much, let's see, how many moles? Here we go. We produced this much lead 2 phosphate. So how many moles of phosphate does that represent? Well, for every mole of this compound, we got 2 phosphates. So we actually consumed 2.66 times 10 to the minus 3 moles of phosphate. Consumed. How much phosphate did we start with? Well, if we started with 1.5 moles of this compound, then we had 2 to 1. No, excuse me, that's wrong. Here we go. 3 moles of this compound, and it's 1 of these for every one of those. So this one is what we started with. Okay, we started with this amount. So we subtract what we used, and we ended up with, let's see, 0.33 times 10 to the minus 3 moles. I know that's not scientific, but it did work. So we have this many moles. So what's the concentration? Well, it's this many moles of phosphate in what solution? 0.03. Yeah, 0.03 liters. Okay, so if we do that division, we get 1.1 times 10 to the minus 2 molar. Okay, move the decimal place 2 to the left. 0.11 molar. That's standard notation. This is scientific notation. Same number. Okay, so much for precipitation reactions. Now we're going to look at acid-base reactions. All right, let's see how close we're getting to the end. All right. We're good. So we're going to discuss acid-base reactions in terms of a Bronsted-Lowry acid. And base, for that matter. In those terms, an acid is a proton donor. And we described acids before as anything that started with a hydrogen, right? So that would be hydrofluoric acid. And what it does is, in solution, it dissociates into proton and chloride ion. So this proton is available to be donated. An acceptor would be something like a base, in which case we have, let's say, sodium hydroxide is a base, and it produces that one plus this one. So how do they react? Well, when they react, these two, right? These two react, but they're actually in this form, so these ions are free to interact. And if we put these together, so we have that one plus this one, yields this one plus this one. Those are all aqueous solution, and these are still aqueous. So these are spectators, here, 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 here. And these are the actual ones that react. This one and that one. This one and that one react, hydroxyl and protons, and give you water. So in an acid-base reaction, the net ionic equation is always that one. Hydrogen plus hydroxyl yields water. Now, we didn't get a precipitate this time, but when hydrogen and hydroxyl react, they produce the water molecule with very little of this left over. The reaction is driven almost entirely to the right. There will be some of this left over, but if we balance the stoichiometry so that the ratios are exactly the same of this and this, then the solution will be neutral. There will be no excess acid, no excess base, and we can usually get pretty close to that if we're careful. And I have to show you how that works, either today or at some future point.
Hydrofluoric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
Okay, you heard mentioned hydronium ion. Oops, there we go. That just means that when you put an acid in water, the proton from that acid, in this case hydrofluoric acid, reacts with the water in solution and produces this ion. They always do that. Protons, pause for a moment. As I was saying, protons never exist as individual protons in solution. Hydrogen ions is a proton. They always combine with water. But as a practical matter, to make things easier, sometimes the reaction is expressed in terms of protons rather than hydroniums. It just reduces the complexity. So it's not reality, but it works and it saves us a lot of footwork. Whenever we need to consider hydronium as a species in solution, we'll explicitly write it that way. Otherwise, we'll just write it as protons, and if it's an aqueous solution, it's understood that it occurs in association with a water molecule. Okay, so when we add an acid to a base, very often what we do is we have a specific amount of one of them in a beaker, and we add dropwise the other one. So say a base is in the beaker, we add acid dropwise, or an acid's in the beaker, we add base dropwise, in such a way that we can keep track of exactly how much of the dropwise is being added. That's called a titration. So how do we keep track of all that? Well, we use specialized glassware. What I'm drawing is a burette. It's a long, thin tube that's calibrated in milliliters and tenths of milliliters. And it starts from 0 up here and usually goes down to 50 milliliters at the bottom. So it will deliver 50 milliliters accurately by this valve control. Okay? So why is it numbered from the top to the bottom rather than from the bottom to the top, as you would see on a graduated cylinder? Because a graduated cylinder is designed to contain a volume. So we measure it as we add. Whereas a burette is designed to deliver a volume. So we want to know how much is delivered as we drip it into our beaker. That's why it starts at 0 at the top and ends 50 at the bottom. So how much did we add? Well, if you start at 0, then you just need to read the amount that's on the side of the burette, taking care that if you come down to, say, 20 here, and this is 21, and your level is in here somewhere, you did not deliver 21 something. You delivered 20 something. Remember, you have to read it from the top down. Common error. Okay, so when we're adding an acid, say a base, let's just say we're adding sodium hydroxide, and there's an acid down here. Doesn't matter what it is. We don't know what it is, maybe. But we do know it's an acid. And we have an indicator in here, which is a small amount of a chemical that will change color. When we reach the point where the number of moles of this equals the number of moles of that, exactly. When we see that color change, we stop adding, and we check the volume. This is known when the equal amount of moles of this equals the amount of moles of that, and that's called the end point of the titration. Okay? Now, this is a practical matter. End point is when we're very close to these equal to these. If we have a way of noting exactly when this is equal to that, not by an indicator, but say with a pH meter where we can measure the pH as the reaction goes, then we can calculate the equivalence point. This is quantitative. This is close to quantitative. It may be semi-quantitative. But this is the exact number. This is the close estimate. We use endpoint rather than equivalence because if we're doing 100 of these titrations, we don't want to run through a pH meter and do the entire titration curve and then find the point on there where they're equivalent. That would take forever. And at least in industry, time is money. So what do? We find an indicator that changes color close to the pH that we know the equivalence point is going to be. So we might do one titration with the equivalence point as our goal. Once we find that equivalence point, then we pick an indicator that will give us the endpoint very close to it. And the margin of error is usually very narrow if you pick your indicator correctly. Now, what do we have here? Let's say we're going to titrate sulfuric acid with sodium hydroxide. How many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid? Okay. The best way to answer these types of questions is to write out the equation. So we're going to react sodium hydroxide with sulfuric acid and it's going to produce water, right? That's a product for every acid-base reaction, and sodium sulfate, which is soluble, right? This is a 2- charge, that's a 1+ charge, so I need 2 of them. Got to write that correctly. That one's correct, -1 + 1, -2, so we need 2 times +1. So now we need to balance it. 2 sodiums on this side. We need 2 sodiums on this side. 2 hydrogens, 2 hydrogens. 1 sulfate, 1 sulfate. 2 oxygens and 2 hydrogens. And 2 more hydrogens means 4. So 4 hydrogens and 2 oxygens, we need 2 here. 4 hydrogens, 2 oxygens. Now we're balanced. So what does this tell us? Well, it tells us that for every 1 mole of that, it takes 2 moles of this. So what data are we given? 1 liter of 0.5 molar sulfuric acid. 1 liter, 0.5 molar sulfuric acid. Okay? So how many moles of sulfuric acid is that? Well, molarity times volume is 0.5 moles of sulfuric acid. So how many moles of sodium hydroxide does that represent? Well, for every 1 of these, you need 2 of these, right? So it takes 1 mole of sodium hydroxide to neutralize a 1/2 mole of sulfuric acid. Was that the question? How many moles of sodium hydroxide? It takes a mole of sodium hydroxide to neutralize a 1/2 mole of a 1/2 molar 1 liter solution of sulfuric acid. Okay? That's acid-base stoichiometry. Okay. Redox reaction. What is a redox reaction? Anytime 1 or more electrons are transferred during a reaction, you have a redox reaction. What does redox mean? Well, it stands for oxidation reduction. Redox is easier to say than oxred. So even though it's oxidation reduction, we abbreviated redox. So what is oxidation? Well, I use an acronym. No, it's an acronym. Mnemonic. I use a mnemonic. You'll get this again in a later chapter. Actually, maybe even next semester. Oil rig. Oxidation is loss. Reduction is gain. So if we're talking about oxidation, there has to be a loss of electrons from the species that loses the electron is said to be oxidized. And the one that gains the electron is said to be reduced. That's where oxidation comes from. Every time you have an oxidation, you must have an accompanying reduction. They always occur in pairs, never separate. So here's a simple example of oxidation reduction. Sodium metal, solid, plus chlorine gas react together to form sodium chloride, solid. Okay, oxidation reduction. Let's be consistent and balance this equation. There are two chlorides. That gives us two sodiums. Now it's balanced. Okay, what has happened here? Well, look at what you have over here. You have a sodium ion and a chloride ion, correct? What do you have over here? Sodium metal and chlorine. Whenever you have the separate element, it is not charged, it's neutral, right? So that sodium has all of its 11 electrons. Whereas chlorine, each chlorine has its 17 electrons. Now that's 17 electrons for one chlorine, and this is 11 electrons for one sodium. So we're talking about individual atoms here. So what do you have over here? Well, if you started with 11 electrons here and now you're a +1 charge, how many electrons do you have? 10, right? You can't make a charge with protons. You have to do it with electrons, either add or subtract. So we subtracted an electron here to give us a +1 charge. We add an electron here to give us an 18. Minus an 18 electrons gives us a -1 charge. So what has happened? Sodium has gone from 11 to 10. Oil. Oxidation is lost. Lost 1 electron per sodium. Remember, if you have a loss, you got to have a gain. Oxidation reduction always come in pairs. So the chlorine has gone from 17 to 18. We have a gain. 1 electron per chlorine. So this is oxidation. This is reduction. And that's what this slide is illustrating. Now, whenever we try to track electrons, we have a method that is used to keep track of those electrons. It doesn't always mean that there's a charge. Very often it does. But we assign what we call oxidation state to each element in the reaction. And when we do that, then we're able to track where the electrons go. Okay, these are the rules for assigning oxidation states. If you have a free element in your reaction, you write the element symbol, such as we did with sodium. That element has an oxidation state of 0. It is neutral. If you have an ion in a reaction, the oxidation state is equal to the charge. So this oxidation state here is 0. This one is +1. Oxygen is given an oxidation state in a compound. If it's combined with something in the compound, it's a -2. The only exception to that is peroxide. So if we have something here, peroxide is 2 oxygens bound together and something else on either end. In that case, -2 is distributed over 2, which means each one is a -1. Okay? That's the oxidation state for peroxide. That's the only exception. Otherwise, oxygen is given an oxidation state of -2. Hydrogen, combined with something, is given a +1. Fluorine is always, in combination with something, is always given a -1, right? Because we said over here, if the element is free like this, it's always 0, right? So if fluorine is in a compound with something other than fluorine, it's a -1. If fluorine were naturally occurring, it'd be F2, and each one of these would be 0, right? So elementals are 0. But in compounds, these rules hold. Now, when you have a compound, compounds are always neutral. So the oxidation state of the compound is 0. That means everything inside the compound has to add up to 0. The pluses have to balance the minuses. If you have a charged polyatomic ion, then the summation of the oxidation states has to equal the charge on the ion. So if you have nitrate, NO3, everything has to add up to a -1. Whatever nitrogen happens to be, whatever oxygen has to be, 3 times, add them together is -1. Those are the rules for oxidation state. Now let's see if we can determine the oxidation state for each one of these using our rules. K2Cr2O7. Polyatomic ion, right? 3 elements, one of them's oxygen. That was the polyatomic. Dichromate. Dichromate has a 2- charge total, if you want to separate it out. But we can still use the rules and determine each of the oxidation states without knowing that dichromate is a polyatomic. We just use the rules. Oxygen is always -2. Potassium forms an ion which is +1, right? And we know it's +1 because it comes from the alkaline metals. So now that we know these, we can determine what chromium is, right? So 7 times 2- is -14, and 2 times 1+ is 2+. That means we have a balance of -12, but we need a -2 charge. No, excuse me. This compound is neutral, right? That's just for oxygen. So the whole thing is neutral. So that means these have to be positive to balance the negative that's left over from those two. See, +12 has to equal -12. So each one of those chromiums that's the total. So each one is +6. Okay? Let's try carbonate anion. This is a polyatomic ion. So we have to add up the oxidation states so that we end up with 2- total. So oxygen is given -2. times 3 is minus 6 total. But we've got to be sure that we have 2 minuses left over. So we can only neutralize a minus 4, right? To leave 2 minus here. So minus 4 is balanced by 4 pluses. So carbon is 4 plus and oxygen is minus 2. I'll let you do the rest. The answers are there. You just follow the rules. You start with the ones that you know. Oxygens, alkaline metals, hydrogen, and then you work your way back to the one that you don't know because it invariably has multiple oxidation states that are possible. And you don't know that oxidation state until you calculate it. Okay. So here's what I told you earlier. Oxidation reduction. And now what we want to do is determine which of these is an oxidation reduction reaction and add a definition. One is oxidizing agent, the other is reducing agent. It's really the oxidizing agent is reduced. So whatever is reduced is the oxidizing agent. And conversely, the reducing agent is oxidized. Okay? So we have these three. Zinc reacts with hydrofluoric acid to produce zinc chloride plus hydrogen gas. Okay, here's a clue. On a test, you want to be able to knock these out quick. So how do you tell, first of all, whether you have an oxidation reduction reaction? Here's one easy clue. If you have an element on one side and it shows up in a compound on the other side, you have an oxidation reduction reaction. Or in this case, if it's part of a compound here, it's an element on that side, same thing. So A is an oxidation reduction reaction. Here we have copper in a compound. It shows up as an element. That's an oxidation reduction. In fact, it's a special kind. I'll describe it in a second. This one is a little more problematic. In this one, you need to determine the oxidation states of your elements. And typically, this oxygen is the same on both sides. Hydrogen is the same on both sides. You can calculate it to verify. The only thing that you really need to focus on is the chromium. Is the chromium oxidized or reduced? Well, if we determine the oxidation state of chromium here and here, we find out it's exactly the same, +6. So the only ones that are oxidation reduction are those two. Now, this bottom one is a special kind of reaction. It's called a disproportionation reaction. Why? Because this compound starts off with a copper in there, and the copper is at -1, +1 oxidation state. It goes two different directions. It goes to a 0, and it goes to a -2. So it separates disproportionately. One of these, see there are two of them, one of them goes to here, one of them goes to there. So you have one of these is the oxidizing agent because it's reduced. It goes from here to here. The other one is the reducing agent because it goes from here. It goes from +1 to +2. Okay? So that compound is both the oxidizing agent and the reducing agent. It's just that not at the same time. Right? You have one of them doing one thing, one of them doing the other. Okay. How do you balance an oxidation-reduction reaction? These are the rules. But it's better just to show you how to balance one. We should be coming down to the wire. We're going to use zinc and hydrofluoric acid as an example. So we have solid zinc and hydrofluoric acid yields zinc chloride, aqueous, plus hydrogen gas. Okay, so we need two of these, and we're balanced. Well, I should say, that's how you balance molecular. We're going to balance it using redox. So, what we have is chloride ions, and that's a bad example because it's too easy to balance without using redox. We need a better example for redox. Let's just look at it up here and see what's what. And maybe what we'll do is we'll focus in on this one for the review session, because there are many more complicated redox reactions that take require a different tactic for balancing. This works in many cases, but not in all cases. And maybe that's the second semester. Okay, so what do? Find out what the oxidation states are. That one's 0, +1, -1, +2 because of the charge, -1 because of the charge, 0 because it's elemental. Okay? So, here we have 2 electrons lost, so it's oxidized. Here we have 1 electron gained, so it's reduced. So we have to balance the electrons. So how do you balance the electrons? Well, if you're going from this one to this one, you need 2 electrons, right? So this is 1 electron per atom. That one's already got 2 atoms, but you need 2 over here. So if we have 2 of these, go to 2 of those, that gives you 2 electrons. Okay? You have to lose and gain the same amount of electrons. So we're going to multiply this by 2. That means we need 2 HCl. And since we had 2 HCl to give us 2 of these for the balancing electrons, we also have to have 2 chlorides. Chlorides didn't change. We just can't create or destroy atoms. So that was the short version. And when we do a review, I think we'll probably have some longer versions of oxidation reduction balancing equations. But for now, that's the end of chapter 4.